Hey guys, today in this video we're gonna solve the Schrodinger's equation for an infinite square well with time dependency. Before that, make sure to like and subscribe as it is free and you can always change your mind later. So first of all, what is infinite square well? So it's all about this potential here, but let's recall the Schrodinger's equation here. And this thing psi here is the wave function. This is the potential energy, and I had to include psi here as well. So this is the kinetic energy, and this is the potential energy. Our goal is to solve for the psi, generally for psi, the wave function here, and which is the main thing that we worry about in quantum mechanics. But how should we solve it? Well, I'm not going to derive the general solution here because this is a partial differential equation. But we can have exact solution for both general solution and other situations. And today's video is about infinite square well with time dependency. As you can see here, the partial t here, which means the partial derivative with respect to time. So the time dependent, the infinite square well tells us that the v of x, the potential energy, is 0 from 0 to L and infinity elsewhere. So infinity elsewhere. So we can imagine a situation that our particle is bound in a box, in a well, and its potential energy is 0 there. So we can suppress this part here. So I'm gonna suppress this part here. We're not gonna be worrying about this part. Just our equation is gonna become h bar partial psi of xt partial t is equal to negative h bar squared, or 2m partial squared psi of xt partial psi partial t squared. So our goal is to solve for psi of t in this equation, but how should we do that? Well, we're going to use a method called separation of variables. We're going to assume psi of x and t to be a product of two variables, which I'm going to call lambda of x and phi of t, which is going to make our work more simpler to solve this equation, and it's going to give me ordinary differential equations. Our goal here is to find lambda and phi and then multiply them together to get the psi of xt, our wave function that we were trying to solve. So let's take the partial derivative of the psi of xt with respect to time. So partial psi partial t is going to be phi dot lambda. So this is gonna be my first equation, and let's take the partial derivative, second partial derivative of this thing here with respect to x, which is gonna be, sorry, I should have written x here. Should have been x, should have been t. My bad. partial squared x partial x squared is gonna be a lambda dot dot and phi. So this is my next equation. So I'm gonna plug these two into my Schrödinger's equation. So IH bar of phi dot lambda is equal to negative h bar squared over 2m lambda dot dot phi. Now what I'm gonna do is I'm gonna divide both sides by lambda phi. So this is gonna cancel out. This is gonna cancel out, and my equation is gonna become IH bar phi dot over phi is equal to negative h bar squared over 2m lambda dot dot over lambda. Now, to solve the problem here, because this side is only dependent on space and this side is only dependent on time, it is equal to a constant, and I'm going to call that constant the energy. So, to solve the Schrödinger's equation with that condition, we need to separate these two equations. So I'm going to call this equation 1 and 2. So the first part, the spatial part, which is a little bit harder, but it's going to be negative h bar squared over 2m lambda dot dot lambda, which is equal to e. So I'm going to isolate for lambda dot dot over lambda, which is going to be negative 2m e over h bar squared, and lambda dot dot over lambda. I'm going to call a constant here, use a constant. I'm going to call it square root of 2m e over h bar, and k squared would give us 2m e over h bar. So lambda dot dot over lambda is going to be negative k squared. Thus lambda dot dot is going to be negative k squared lambda, which is going to give me this differential equation, which has a solution. That is, the solution is lambda of x is equal to a sine of kx plus b cosine of kx. Now remember the boundary conditions that we had here. Lambda of 0 is 0, and lambda of L is equal to 0. Now let's plug in lambda of 0. Lambda of 0 is a sine of 0 plus b cosine of 0, which is 0. So sine of 0 is 0, thus I'm going to get b cosine 0 is 1. So I'm going to get b equals to 0, thus lambda of x is going to be a sine kx. Now let's plug in the second boundary condition. Lambda of L is going to be a sine of KL is equal to 0. And therefore sine of KL is going to be 0, which means that KL should be equal to n pi, any integer times pi, and my K should be equal to n pi over L, and the lambda therefore should be a sine of n pi x over L. Now Let's go back and find this constant here. So we need to use normalization, which is gonna be this thing right here. So lambda conjugate is itself, because our spatial part is real. Therefore, it's gonna be a squared sine squared of n pi x over L dx is equal to 1. And if you solve this integral, a is gonna be root 2 over L. So our lambda of x is square root of 2 over L sine of n pi x over L. So this was our spatial equation here. For the time dependent part, we had I h bar phi dots over phi is equal to e. So this is easier to solve. I'm just gonna, this is separable differential equation. I'm gonna just show you how it is solved. d phi phi -1 e dt over I h bar. And if I integrate this thing, I'm gonna get ln of phi to be equal to et over I h bar plus c some constant of integration. And if I exponentiate it, I'm gonna get phi to be equal to some constant to the power of et over I h bar. And if I move the I to the numerator, I'm gonna get negative I et over h bar. And this concept of integration can be absorbed to the spatial normalization. Thus I'm gonna be able to say that phi is equal to e to the negative I et over h bar. So this is my spatial, and this is my time dependent form, and my spatial form was spatial solution was this. I remember that psi was the product of these two, and thus I'm going to be able to write it as, finally, square root of 2 over L sine of n pi x over L e to the negative I e and t over h bar. Explicitly, I'm able to write it as 2 over L sine of n pi x over L exponential of negative I h bar squared pi squared, negative n squared pi squared h bar squared over 2m L squared. So this is my full solution for psi, but we can make it more complete by saying that it can be superposition of x and t of different linear forms. So I can be able to write it as square root of 2L, the infinite sum from n equals 1 to infinity of Cn sine of n pi x over L into the negative I e t over h bar. And that is the final form of the wave function for the infinite square well with time dependency. And we can also write the energy. So from this we can remember that k squared n was 2men over h bar squared, and isolating for en would give us h bar squared kn squared over 2m, and en would be equal to n squared pi squared h bar squared over 2ml squared, which tells us that energy is quantized. So we've also found the quantization of energy here. And energy is quantized, as you can see, E1, E2 is equal to 4E1, E3 is 9E1, and so on. So this tells us that energy is quantized here. And if you plug in this equation and take the partial with the partial derivatives, it would satisfy our initial equation. That was IH bar partial psi of xt over partial t is equal to negative h bar squared over 2m partial squared psi of xt partial x squared plus v of x psi of xt. So this thing right here, this psi of xt, would satisfy this equation, and therefore it is a solution to this equation that we've written up here. I'm sorry for the mistake that I did here. I switched up the spatial and time derivatives here. But this is the solution to Schrödinger's equation for an infinite square wave with considering time dependency. Thank you for watching this video. Please make sure to like and subscribe. I'll see you next video.